I believe Robin shared a link to like a GitHub where you can find the Python notebook that I've been using for today. So yeah, if you guys want to, then you can go and download that notebook and run on your laptop or on Google Colab if the internet is working. I'm not sure the status of the internet is. Okay. Is the internet not working for most people? By yes, you mean it's not working, right? It's my fault. I should be asking questions that lead to double negatives. Well, okay. So, lecture 2 for me, I guess 3 for you guys today. So I'm going to start with just maybe listing some popular ML algorithms. Anybody knows what KNN is? Louder, please. Alright, yeah, it's just K nearest neighbors. And I guess you could say this is one of the simplest machine learning algorithm. Just literally looking at your neighbors and whatever value your neighbors have, that's the answer. That seems quite simple. Logistic regression, although the name is kind of misleading because it's a classification algorithm, but we call it logistic regression. I think it's a bit silly, but I didn't make these names. So support vector machines. Yeah, this is you can do both classification and regression with it. Same thing with all the other flavors. You can do both classification and regression. So what is? Does anybody have a favorite amongst these? And can you tell me why? Anybody? Anybody have a favorite ML method? Who? Nobody? Nobody has a favorite? You're smiling. Maybe. What's yours? Random forest? Yeah, that sounds pretty. Yeah, it seems nice. There's a forest. It's a bit random. Anything could happen. Yeah, it sounds quite exciting. Why is the rand? Why is the what's the? Why is it called a forest? Right. When there are a lot of trees, it's a forest. That sounds pretty logical. Why random? Yeah. Yeah. There's few different points of randomization there. One is it's an option in most packages. You can either do it or not do it. It's called bootstrapping. Every tree you can train with a bootstrap sample, which is about 67% sample of the data. You can do that, or you can also even at every node of the trees there's some notion of sampling because depends on how it's implemented. I think random variables could be picked for like splitting and determining what good splits are. So there's yeah, I think that's the name. But although I don't know for this term, just speculating as well. Boosted trees, and we know what boosted trees is. Why is it boosted? It's not because people are drinking boost there. That's one thing I think we can eliminate. Oh well, I think. Yeah, and maybe and you've heard of neural networks and deep learning. These are the most these days. These are the most powerful sort of machine learning methods. But I think we have to be mindful that. So can anybody tell me one application domain where, despite having large amount of data, actually neural network is not the best model, even if you have a lot of data? Anybody knows? Embedded systems. I mean, that's not really, well, you're probably thinking maybe in terms of, in embedded systems you need like smaller sized models, and yeah, you could say that, but let's say maybe that's not a constraint. So if somebody here you had something, sorry? I didn't quite understand, but maybe you're talking more about in certain situations there's like questions of ethics and no. Sorry, I didn't. My question was what in what maybe in healthcare domain there are other models better than neural networks. Okay, never mind. So one particular data which is called tabular data. If your data has a tabular structure, uh, I don't work with this kind of data, but I know that there was actually a paper recently where there was actually a neural network model developed where it operates on tabular data, but there is no training, or I don't know how to describe it. It's a auto trained neural network. Maybe somebody will get into detail in this next 10 days, but uh, you don't have to. It's quite fascinating. But except maybe this one most recent advance in tabular data, where there are like well-defined columns and there may be some strange or complex tabular relationships. Um, it seems that boosted trees are the best, and in many like simpler applications, boosted trees seem to be quite good as well, especially if the data size is not crazy big. But with images, with text, and many other more complex kind of data where the structures are much fuzzy and and so on, I think neural networks are the best model hands down. Okay, so let me start with simplest uh, sort of model, logistic regression. One of the simplest. Not I wouldn't say KNN is the simplest. Before I get into this little bit more, let me ask you a question. Is linear regression a machine learning algorithm? Show of hands for yes. No. Is linear regression a machine learning algorithm? No. Who says no? Who says yes? Okay, we have some yes and a lot of no response. Yeah, it is a machine learning algorithm because the point is you have some data and you infer some parameters from the data, then you make a prediction. Even though it's a very simple model, it's still a machine learning model. And logistic regression is just it's a way of it's pretty much it's a linear method. Uh, you have two sets of data. Let's say this is a class A and this is class B, and you want to classify this data, which essentially means you want to draw like a decision boundary that separates these two data into two different modes. This decision boundary is linear. That's why we call this a linear model. Now, but you may ask, oh, but then there's this sigmoid component where there is this like you're taking, you're doing something like this. This is clearly not a linear function. So how is this still? Is this still linear? You may ask something like this, but this part is only to convert this portion. Let's call it the score into a probability, and the decision. What makes a model linear versus non-linear is the decision boundary, and not how you compute the probability out of the decision boundary. So that's, I think, maybe something to remember. Like so what is this function called, by the way? Does anybody know? Sigmoid. Wow, you guys are quite familiar. Yeah, this is the famous sigmoid function. What is a nice property? Anybody know what's a good property of sigmoid? What's not a good property of sigmoid? Why is sigmoid good? Anybody has an idea? from 0 to 1, but uh, so that's not, that was, but 0 to 1, not 0 and 1. Okay. Anybody knows why, yeah, sigmoid's nice and why it's not nice?
Every data we pass to this function will result answer between 0 and 1 to give the probability.
Yeah, that's a nice feature. Another nice feature is it's continuous and nicely differentiable. Very nice, well-defined derivative, and why, and that's important. We'll come to see later. Yeah, so that's a nice feature. Anybody knows what's not a nice, very nice feature? It's very what? Well, the function can't be slow or fast. I know what you're saying, but I think what you're saying is if you use sigmoid's activations a lot, your training, neural network training can be slow because at the extremes the gradients are very small and your model may not update at all. Okay, let's move forward. I just since you guys seemed so familiar with the sigmoid and you all said sigmoid, I thought maybe you guys knew more, but I think there's something to learn. Okay, so before moving on, so essentially, okay, we have this sort of formulation. We want to find the optimal parameter beta that sort of gives us this nice separation that draws this linear distance boundary. So the problem, the problem here, what we're trying to do is we are trying to figure out what is an appropriate beta to classify this data. Does that sound good? That's what we call fitting a neural net, like a model is called. That's what we mean when we say fitting a model, right? It's essentially estimating the parameter that gives us something optimal. So our task is to figure out what beta is. Now, how do we do something like that? I mean, one of the here you may have, some of you may have already heard about gradient descent. But what could be another strategy where you can do this without doing gradient descent? So you had some ideas? It is a hyperparameter tuning. Yeah, you could say that. So, but then how do you do that tuning? You try a bunch of different numbers. Okay, anybody has any thoughts on how to do this without gradient descent? Sorry? Minimization? Yeah, so actually I've written it here. You can, let's say if it's not a very high dimensional problem, let's just say this is one dimensional. In this case it's two dimensional, but let's say it's simple, one dimensional. You could just go from like minus 100 to 100 with like with like 10,000 points between them. You can try all of them and see what gives a good result, right? And there, what you said could be helpful. You could have a held out validation set where you test that. Then it, kind of becomes like a hyperparameter tuning. But actually, in reality, you don't want to do that. You want to treat it as a proper parameter and then tune it as a and treat it as and then use a different method. So yeah, I mean, doing something like that would be effective only in a very low dimensional setting. So what you want to do actually is do this thing called gradient descent. Now, what gradient descent is imagine this parabola, right? How many of you are familiar with gradient descent already? We have some. We have maybe a large number of you are still not. Okay, so let me give you an intuitive explanation of what gradient descent does, right? Okay. Let's flip it first and let's think about. So let's say I take you to the foothills of the Sivapuri mountain, okay? Out there, like maybe 8 kilometers away or something. I don't know exactly. Let's say you guys have all been to that area, like the temple, Budal concept is there, right? Let's say you start out there, and I blindfold you, okay? And I tell you, oh yeah, just go to top of this mountain. Do you think this is an impossible task or a possible task? Possible? Yeah, who says possible? Okay, tell me why. Sorry? Yeah, you can wherever you are, you can scan like a small area around you. You can walk around, right? You can figure out which one. You just have to keep going upwards. You're here, you go, you scan a little bit, you go up. You scan a little bit, go up. You should keep going up. Now, where would that assumption fail? Yeah, if there was another little peak, and maybe you go to that peak, which is like not the main peak. You go to the side peak. You'd still reach the top of some mountain, and you'd probably still have a nice view, but you would not reach. But let's assume this is a nice, well-behaved mountain and only one peak. Then you'd reach the top, right? So it's essentially we're exploring this. We're using this. This idea is called gradient descent, and instead of taking scanning like area, what you can actually do is always move in the direction of like the gradient. So in 1D, it's quite easy to visualize what that would be. You're here, and you can compute the in math. If you're doing computationally, you can compute the gradient in multiple different ways. You can, if it's a well-formed function like this, right? This is a parabola, right? Can we know the gradient of a parabola? Yes? No? Yeah? If y equals x squared, what is the gradient? 2x, right? So I mean, this is not exactly x squared. It's probably like x minus 3 squared or something, right? It should be pretty easy to. Maybe there's an intercept as well. It should be pretty easy to compute the gradient. So for like a well-defined function, we can have closed. We can have the we know the gradient already, so we can just use it. And yeah, we just keep moving. If we move in the direction of the gradient, we will be doing gradient ascent. If we move in the opposite direction, we will do gradient descent. So this function here is, anybody knows what this function is? Huh? Louder. Brian, yeah, who said binary cross entropy? Yeah, that's correct. So yeah, this is essentially for classification, for binary classification problem, this is one of the most widely used cost functions. What else could we use for? What would be another cost function we could use for binary classification? Yeah. So yeah, but which one would you prefer though? Binary cross entropy, right? Because yeah, I think for classification, that is preferable to mean square. But you can definitely use it. For simple problems, I don't think it makes a difference. So yeah, you can set up your cost. So this is the binary cross entropy function, and you can compute your derivatives. You can compute your gradient with respect to the cost function, right? So just pay attention to these parameters. Like your cost function depends on. Actually, I didn't write it here, but it depends on x, y, and beta, right? Beta is a parameter we're trying to estimate. The gradient of interest is just with respect to beta. We don't care about how this is changing with x and y. Y is practically a constant, and x interacts with beta to give some value for probability value, and you're interested in how beta changes. Changing beta changes the loss rate. So yeah, and this is just the gradient, and this is the final piece where your updated beta is just beta minus the learning rate times the gradient. Any confusion here? I think this so far should be chill. Okay, I'm not going to spend too much time here. If you guys remember, if you guys are reasonably comfortable with your derivatives, you can very easily guys are probably better than me at doing something like this. It took me some time because the reason was, I actually tried to, I was obviously I'm not going to do everything from scratch. I was trying to find out the derivation for the gradient term, and I didn't find it in the internet. So it was just used, and they just said, oh yeah, you can derive it yourself. And since I didn't find a good resource, I did it myself. And, it's a bunch of steps, but in the end, the derivative is quite simple. It's just x times the probability of x minus y. So yeah, that's what you can do as well. You just have to use a lot. Yeah, I wouldn't expect people to memorize or like this, but just use it when the time comes. So just a few things on gradient descent for simple problems. You can just initialize with some like normal, random, or zero. Uh, but uh, why is this initialization thing? But for some complex problems, this initialization can have some consequences as well. Because in the earlier example of Sivapuri, right? What's the initialization? I left you at the Buddha temple. Instead, if I left you here, I think you would suffer quite a lot, right? You may not reach. Highly unlikely that you would reach the top there. So I think there are problems like that where the initialization is also important. Compute the gradient, beta equals this. We've already seen that. And oftentimes, the algorithm is something like this: compute the gradient, update your beta, and terminate if the magnitude of change is too small, like you're not learning anything new, you sort of reach a stable point, or after a certain number of iterations. Because oftentimes when you're actually implementing this in real life, you can't have your code running forever, right? You get stuck in like a local maxima or minima, and you may just be running forever. So you don't want that. So this is normally like this is the sort of the algorithm, so to speak. Generally, in complex problems, you adapt your learning base. You make it high in the beginning and low later on, because your gradients are higher in the beginning, and so yeah, many things need to be. Most of these things have to be adapted based on the problem. So by the way, this is my nice little attempt at animation. So this is your original problem, and this is your separation problem, and yeah, I basically implemented like this gradient descent, and I wanted to like, I was curious, okay, like how long does it take, and so on and so forth, and obviously this is my implementation, right? Maybe your implementation can be so good that you reach a stable point in like after 100 iterations. That's entirely possible. Depends on. Well, here for like logistic regression, there isn't much, too many things to play around with. Maybe just the learning rate and the adaptation of the learning rate. That's something you can mess around with, play with, and achieve good results. But here, if you're seeing this animation, the decision boundary kind of stabilizes after maybe like 4,000 iterations or something, and the maximum is like 10,000. After I think about 4,000, 5,000, nothing really changes. This is typically what you see in training, models. In the beginning, everything was classified as one class, and slowly, like it got better and better. And yeah. Okay, so I'm just gonna go through. Yeah, we just looked at a linear model, like a very simple one. We were able to actually implement it and run that, train that model, and use it quite easily, right? It wasn't very like not even like 100 lines of code, I think, here. So so that is possible. However, for more complex problems, linearity is not enough, and this is a very simple illustration transform your variables, you apply nonlinearity using these things called kernels. And then, but in this nonlinear space, you're finding linear decision boundaries. So if you're just thinking about the final decision boundary, that is linear. That's always linear for SVMs. But the overall outcome is nonlinear. So with that, I hope that well. So let me make it a little bit simpler. And the way that nonlinearity is applied is by applying this thing called kernel trick, where you actually don't transform the entire variable. What you do is instead you only compute distances in that kernel space, and essentially, actually, again, the sigmoid kind of like something is not exactly sigmoid, but an exponential function or polynomials. You could use RBF, radial basis functions, which are kind of like exponentials. Yeah, more and more you do probability stats, machine learning, you see like exponential and like normal distributions feature all over the place. So yeah. Another thing about SVM is we have this thing called hard margin and soft margin SVM. Does anything know what the difference is?
Yeah, I think like the inner nearest use soft margin you can take the all the data points.
So uh, yeah, not quite, kind of. So okay, I think this picture actually demonstrates it quite well. So on the left, what we have two data points, data sets, which are quite clearly separable by a linear hyperplane, right? So in this sort of case, we can find this margin. M is called the margin. Uh, that that's the minimum distance that has to be satisfied between any 2 points, points belonging to these two categories. And but in practice, this is almost like in real life noisy data. This is almost impossible to achieve. So you often end up using soft margin SVMs where in the hard margin, in this margin, it's kind of like no man's land. Okay, it's like the border between India and Pakistan. You can't have your soldiers here. Whereas here, you can have some of your guys not cross this boundary maybe, but you can have them. And this is a form of regularization actually, because if you're too strict, even when this is actually achievable. This is if you try to force your algorithm to be like this, it may not be good. Some kind of variable. Sorry? Read the question. Yeah, can you explain? What is Ridge regression first of all? Wait, so to simplify further, in what setting is Ridge regression used? What is it most similar to? What's even a simpler version of Ridge regression? Just linear regression, right? It's a linear regression with lambda parameters, like with regularization. So yeah, we don't even need to, but you're on the right track. You don't even need to do the regularization. Linear regression gives some notion of variable importance, because in linear regression, you get a value, like a weight or component for each of your variable, and that can be, particularly after you've done normalization. If you don't do normalization, then it's a little bit nonsensical. If you've done your normalization, then that kind of becomes your variable importance as well. So what does ridge regression do then? Why is it helpful?
It helps to eliminate the feature database for the model.
Yeah, you can use it in that way. suppressing the you're penalizing the weights to become from becoming too large, and that sort of stabilizes your model a little bit. Any ML model, and but then if you actually do L1 normalization, regularization, sorry, then a lot of your weights become zero, and then you can just get rid of those. In principle, it doesn't always work, but when it's working, you can just get rid of those variables with zero importance. And there's actually very nice, elegant math as to why the L2 norm does what it does, and why the L1 norm leads to sparsity. It's quite fascinating. So if you ever have a chance, you can explore that a little bit more. Or we can talk later also. I can also explain, but maybe not right now. Thank you for. Oh yeah, so we're almost out of time. So the last key piece before you guys get more and more into like the more other like major like the topics tomorrow is so we looked at gradient descent. But for neural networks, there's one more thing to think about, one more thing to sort of like take care of, which is that um, we don't. So okay, in neural networks, what we often have layers, right? We have a lot of layers of weights, and it's quite easy to compute the gradient and update the parameters in the final layer. But if we were to compute the gradient with respect to the loss function all the way back from the final to the first layer, it would be quite a nightmare if you want to do that like directly. So what we do, so you can actually use some obviously it's based on some pretty nice mathematics. It's based on chain rules basically, chain rules of derivatives, and essentially then you compute the error in the final layer, and you can propagate these errors backwards by just multiplying by the weights. And this step is called backpropagation. It's propagation of the error. What is the error? Error is just the difference between what you're trying to predict versus what you're predicting right now. And you just keep multiplying on when you come back from the last layer to the first layer. You keep multiplying the gradient by the weights of the previous term. Well, it's essentially this second equation that's the key, where your error at layer L is weight at L plus 1 times the error at the previous layer. So essentially, this allows us very easy and efficient computations of these gradients. And this also motivates some thinking about what happens if these gradients. We have two issues when we train neural networks. Things that happen often. One, your gradients blow up. We say that sometimes. In another occasion, your gradients vanish. Right? These are two canonical problems. Anybody knows what that means? Exploding gradients and vanishing gradients. As the name suggests, it should be kind of obvious. Sorry, you said zero gradient, something like that? Yeah, if your gradients are really like small, then the more back propagation you do, you're just multiplying even like smaller numbers by more small numbers. So you're essentially just making your gradients zero, and when your gradients just zero, you're not learning anything, because the learning rule is always it's this your u beta is beta minus learning rate times the gradient. So if your gradient is zero, you're not learning anything, you're not updating anything, and you could be stuck in a local minima. Another problem is exploding gradient. Yeah, if your gradient is too large as well, you're just gonna have like explosion of gradients, and you're gonna have like floating point errors. So So, but there are oftentimes there are some pretty simple tricks that are used in actual networks to like not have these kind of problems. Uh, Things like batch normalization is done. Uh, you people and we all nobody very only in the last layer for classification we use sigmoids. Or only if it's a binary classification problem. Actually, not even in other things. We have multivariate classification, multi-class problems. We use softmax. So we don't use sigmoids. We use sort of like we use things like ReLU and many different variants of ReLU, which where we don't have this vanishing gradient issues. Yeah, this is just this part written out. I mean, I think you're gonna learn more about these things in other lectures. So I'm not gonna. We're out of time anyway. So yeah, maybe when there's in the lab exercise today, I have maybe we can look at these things if there's time. But for now, I think we're done. Unless you guys have questions. Is recall and precision same? No. So sorry. Maybe you saw this here. Is that true? Um, well, this is a bit of a silly problem. So in this, if I compute the precision, because there's a perfect classification, both of them is going to be one. But recall is it's called. Let me write this out for you. So recall is true positive by true positive by. So out of all the positive examples, how many did you label as positive? And what are the total positive examples? The total number of true positive, which means it's the model and also predicted as positive, and false positive, which means actually it's false negative because the model predicted it as negative, but it's actually in reality it's true. So that's called a false negative. This is recall. And precision is of all the things that the model said was positive, which includes the false positive. What percentage of those are truly positive? So these two are both important. So recall is it's like when you go to the doctor, you want both. Obviously, you want everything to be good, but you want recall to be high. If particularly if it's like in its initial test, like in a lab test. Okay, there's some your platelet count is low or something. You want in that kind of situation that to have a high recall, even at the cost of low precision or specificity. Even if they get it wrong sometimes, it's more important that your like high platelet count is maybe flagged. Because then you do another more better test. Maybe not. I'm giving a bad example, but in a simple test, in a simple diagnostic test, it's better to have high recall, and it's okay to have lower specificity or lower. Let's say it's a biopsy. It's a biopsy, and then you're making a decision whether someone has cancer or not. There, if you say if you tell somebody you have cancer, you probably ought to be like near 100% right? So in that case, it's maybe almost okay to say have a little bit low recall. Because if somebody has this is not like my judgment, but I'm just saying maybe I could be of the opinion that if I had cancer, if they missed it, maybe I'm happy like. But if somebody else might have a different opinion. Maybe they're very careful about their health, and maybe they're more upset. I would be more upset if they wrongly flagged me as cancer than if they missed it in like if the chance of missing it is relatively high. So there's always a trade-off in these sort of situations. You can't have perfect recall, perfect precision, and perfect specificity, but depending on the situation with that.